No, it was due at 1:40. I still have 7 minutes. Why is it?
Okay, let's start.
The screen's getting all stuttery, so
We need to shut that line, the third glare on the front.
I noticed that that's not bad.
You want me to? I thought I started talking. Do we need to set this line? Is there a glare on the front?
No.
It's not bad.
Okay. All right, so did I show you this before?
Yeah.
It's still cool enough to show again. So this was, Dr. Thompson, Yoda, Jedi Master, created this. And so view 0 is just the original piece of paper, which you can maneuver. You can change the width and the length. And then view 1, so you can use, so this is a really common use of sliders, is you can set up a slider to change the view, and you'll be doing that. And so it's just a matter of if statements. So you can say, create this visual, telling GC to graph such and such if view equals 1. So then if view equals anything else, you don't see it. And then when you put view on 1, that command line, is activated. So it's very easy to do. So in view 1, no, that's not what happened here. In view 1, you can see the square cutout, and you have a slider to maneuver the width of the cutout. And then in view 2, you can take away the squares, and you can see the flaps, and you can fold up the box. But what's cool is you could fold it up, you could go back to view 1, and you can leave the corners there. So it really gets you to understand the situation. So, right. Oops. And so they're smaller. This is the box you get when you have the smaller cut. Okay, so extra credit. You want to try to make this?
Seriously?
Seriously, sure.
How much?
A in the course.
Are you serious?
Yes, I'm serious. I'm very serious. A+ in the course. Go for it. But this is a required assignment that will be due upcoming. Okay, so this is the same idea of the sheet of paper, but this is just showing the effect of changing the square cutout size. So here I'm showing the paper, and then this bar, well, we'll see what the bar does in a second. So as I slide the end slider on this one, it's as if I chose square cutouts now and cut those out already. And so the pinkish part is representing what quantity? If we imagine folding the flaps up to make the box, what quantity is the pinkish bar representing? Length of the resulting box. And then what's the blue bars? Height of the box or length of the cutout. Okay? So this is going off the similar idea, but now this is going to be you've got all the tools now. So with all the assignments we've done so far, you have all the tools to come up with something like this. And then as an added element, it's in how few command lines can you do it. So the fewer command lines you can do it, the better. Okay. So the task is to get it done. Okay. But then an added task is, can you think about how could you reduce the size of your file to create the same thing? What you can't see here is, because of the screen maybe on the back, I have it in gray, so it's not showing up, but I have gray lines here noting where you would fold on the flaps, and that is required as well.
Can you max out and whatever the max is?
So let me talk about how that works. For an 8.5 by 11 sheet of paper, that's basically 3/4, so 3 to 4 ratio. So you can build this based on a 3 to 4 ratio, but then your n has to represent the number of inches for your square cutout. Okay, so right now it's at 0.52. There's a square of 1. Okay, so you can use maybe there's some different ways to do this, but you can use a 3 to 4 ratio width to length because that's very close to. I think a piece of paper is like 0.77 is the size of the width to the length. So that's very close to it. So we can use 3/4, but your n has to show number of inches of the side of the square cutout. Does that make sense? Okay, so that's you're ready to start working on that. And I have a little video that I made just explaining this one. I'll put the link on the video on the Blackboard. Okay, that's one thing that you're working on. Another thing that you're working on is so in the second half of the course, and your major component of this course is a project. So we want to start thinking about what you'll do for your project. I can't get that to turn on. Why isn't that turning on? Here, rewind. Ah, one of those. Internet. Blast. Come on. Anyway, okay, there we go. Here we go, final project idea. So we've done those 2 readings, the Smith lesson protocol and the five practices. So this will be due a week on Tuesday. This is Tuesday. So you're going to build from these previous 2 readings, propose an idea that is important for high school algebra or pre-calculus students to understand, explain the understanding that students should have, and make an outline of a sequence and tasks that will support students in developing that understanding. Okay? Do not think of these tasks as test questions, rather think of them as discussion questions that you'll incorporate into your lessons. Okay, so referencing number 1. Your idea topic must be in the realm of variable, covariation, and or function. Okay, which is almost all of pre-calculus. But something, so the whole point is, this is what GC is the strongest with, is covariation and function. Topics in pure geometry, especially the Pythagorean theorem, are not allowed. So one semester I opened this up and we had three projects on the Pythagorean theorem. So we're not, no Pythagorean theorem. Okay, so, and you're gonna bring a hard copy of your proposal to class on Tuesday. Okay, so this is last year's. So it's the exact same thing, it's just to get thinking about what would you want to do your final project about, which is I think 40% of your grade, is that right? Big chunk of your grade. So we gotta come up with an idea. Many of you have been involved with the Pathways curriculum, so you have a whole realm of choices. You can most of what's in there would be great. Okay. If you're not sure if it falls under this category, but you think it might, you can just ask me. Before you do a lot of work on something, then I'm going to tell you, no, this doesn't qualify. Just make sure you ask me. Okay. Questions about the final project? This is just the idea phase. Idea phase, yeah.
So, like, the hard copy that we bring in class on Tuesday, will we get to take that home again with us, or should we make a copy for ourselves, too?
Oh, yeah, do it on the computer so you have an electronic file. Yeah. So you have, yeah, so this is going to be ongoing. I'm going to give you a sequence of tasks throughout the rest of the semester towards working on that. Other questions? Yeah.
Can we, if we start building and working as it progresses and we want to change it, can we change our idea, or we kind of
yeah, this is just your, like a brainstorming phase. Okay. But kind of consider it that this is what you're going to do. So you want to do something serious. that's a real possibility that you could do this. But there is potential for changing.
For number 3, I'm just kind of confused on
Okay.
what exactly you want. Is it like tasks, like things that we'll ask them to do, or just questions that we'll ask them while we're presenting the idea?
Outline a sequence of tasks that will support students in developing understanding. So it's kind of both. So it's like what will the lesson plan, how will it unfold, and that's kind of almost the same as what questions would you want them to be, to discuss and be able to answer along the way.
Okay.
So it's kind of both.
Okay.
Good questions. Any other questions?
Does
Okay.
it have to be in paragraph format? Is it just kind of bulleted or?
No. Well, explain the understanding your students should have can't be bulleted. Yeah, I mean you have to write it out.
Yeah.
But then number 3 is, it's like a bulleted sequence, but you're not just going to write phrases, right?
Okay.
You're going to write out questions and full sentences. Each bullet might be a small paragraph. Or something like that. Yeah. So expand.
So in terms of the final project, are we like showing it to our class, or I mean, it's obviously we're doing a GC file.
Yeah, you'll have a presentation at the very end.
Okay.
You won't be executing the teaching, but you'll be presenting about your plan.
Okay.
You do a presentation to the rest of the class. This is how we chose to create this lesson, multi-day lesson. Yes, ma'am.
I just want to double check on this, but like the whole point of this is like incorporate graphing calculator, right?
Yes.
Okay.
Graphing calculator is a required element. No, I'm glad you asked. I'm very glad you asked because this is, the whole point is to incorporate graphing calculator. That's why I'm saying let's do pre-calculus, let's do stuff with functions. Yeah.
Was this a group project or individual?
This is individual.
But the final.
Just pretend you are doing a project. This is what you're going to do.
Okay, since we're supposed to build from the previous 2 readings on those, this weekend we're just brainstorming on ideas what we're going to be doing. But when we come to the final idea, are we supposed to be saying like, okay, this is how I'll incorporate this lesson with the 5 practices from the Stein article? Like, should I go say, okay, now at this point in my lesson, I would go and I would monitor students, or is it really more about, okay, this is a tool that I can use for my students? So the project you want to be incorporating these practices, and so that will come through as you actually get into the details of designing how you're going to enact the lessons. But that doesn't, you can think of that in a broad sense here when you write this, but you're not going to get into, and here does not get into the details of those things. So that's a framework. So in a broad framework, you're considering that as you do this first assignment. Then, as you're really laying it out, then you'll get into the details of those. Okay.
So, does that answer it?
It does.
Okay. Okay, and then we have the 4th article will be due a day from today. Okay? A week from today. So that's the 4th article, and that one has not only the critical précis, but then some reflection also. Okay, and I'll give you the details on that.
Are you gonna post that today or?
Yes,
Okay.
yes. Cool. Other questions? Okay, so I want to go through. I want to take you through. So 482. Those who had me for 482. Did I take you through the painter? Do you remember this, painters? Oh, good. Okay, good. All right. So you're going to be this. I just did this a week ago in calculus. I taught this lesson, so I'm going to teach it to you. So you're acting as students, so you're thinking about being a student in the class, but then you're just also monitoring, keeping a second view, a second hat on, where you're monitoring what I'm doing and how it's affecting you and how the lesson is unfolding. Okay. So we got 2 painters that started painting their respective houses. At a certain point, the first painter is
has already painted 250 square feet. The second painter, we'll call him P2, has already painted 400 square feet. So my first question is, how is this visual that I'm showing here a representation of the original problem? How would you say this visual is representing the problem? Michael.
Kind of like a sideways bar chart of how many square feet they painted. So bottom line would be 250, where each of those columns represents 100.
Okay, so he's saying this bottom bar is a quantity. The length of that bar represents, what do you think it represents?
250 square feet of house being painted.
So in general, what would that bar represent? Number of square feet painted. Is that it? Yeah, right. So this you're looking at by P1, right? And therefore, and he's saying right now that's representing this 200. The length of that is the 250 square feet painted by P1, and so this one would be
Number of square feet painted by P2.
Okay. So what I'm going to do is painter 1. So they're painting simultaneously. And so painter 1, I'm going to show you how painter 1 is going to paint 200 more square feet, and we're going to see how also the additional amount that, or how much painter 2 paints. Oh, I had it. Ah. Got it. Okay, so why might I be showing now the bar's thinner here? What does the thinner bar possibly represent? Tyler?
I think the thinner bar just helps you to see the difference between what's now being painted, whereas where you were started, that was the original versus now it's changing.
Okay, so we had an original amount, and now we have a kind of a new amount. So that thin bar represents change. So let's make this. Let's assign the variable y to be the number of square feet painted by P2, and we'll say x is the number of square feet painted by painter 1, and so therefore this short bar is delta x, and this is? See? Okay, so my question is, is the total amount painted by painter 2 the total amount painted by painter 2 the same size relative to the total amount painted by painter 1? Is the relative size of the total amount painted by painter 2 being maintained relative to painter 1? Alex?
I would say no. Painter 1 is painting more quickly than painter 2.
Painter 1 is more quickly than painter 2. Tyler, what do you think? What do you say?
I think that the total distance the first time was 400 to 250.
Okay.
And now it's more, but the ratio's not the same.
Okay, so I want you to. So a couple of people are saying no. Anyone think yes? Well, anyway, so if you think no, then or yes, I want you to prove it. Prove it mathematically. So give me some mathematical proof that the total y relative to x is staying the same or is not staying the same. Can you give me some proof? Mathematical proof. Okay, Miguel. What do you think?
I think that it's not the same.
And what was your proof? You were
The proof was
mathematical proof.
that the ratio between them is different. So the first time when you have well, 400 total,
Okay.
was going to be 250 over the 400,
Okay.
and that ratio was different compared to the delta x and delta y, which was 200 over about 250. It looks like.
Okay, so you compared the 250 and 400 to 200 and 250?
Yes.
Okay, so is that, what do we think? What is your reaction to that? Molly?
I believe we did it a little bit differently. We looked at the original ratio, so the 400 or 250 over 400 compared to the overall amount that they've done.
So what was
650
650 and
under
450? So you compared the starting amounts to the change, the ratio of the starting amounts to the ratio of the changes, and they compared the ratio of the starting amounts to the ratio of the new total amounts. So which, is it either way okay, or if we want to talk about it, is the amount painted by painter 2 relative to painter 1, is that staying the same? Is either way okay? I think we have to look at total amounts, right? And we have to, because we don't know what happened before, right? We're not sure what happened before the starting value. So we can't assume anything prior, so we need to look at total amounts. So is it safe to say that you used some numbers here? You used x is 250 and y is, and then x is, and y is. And so Molly, what did you do with those numbers? Is that those the numbers that you looked at?
Yes. We took 250 and divided it by 400.
Okay.
For the first ratio, and then the second one was 450 divided by 650.
Okay. So you looked at x over y. And did you get values?
Reduced to 5 over 8
And
and 9 over 13.
not equal, right? Okay, what about the size of the change in y relative to the change in x? Does that maintain a constant? So the total painted by painter 2 relative to the total painted by painter 1 does not, that's changing, okay? What about the change in the amount, change in y relative to the change in x? That's staying the same? They're saying need more information. You guys agree? People are nodding their heads. Okay, so let's let painter 1 paint 300 more square feet. 1, 2. Let's see how long this takes me this time. Got it. Okay. So actually, I need to mark off some points here so you can go. So you guys are, here's where we started. And then we had this. And now here we are after another 300 painted by painter 1. Go. So now I want to ask about the change of the amount painted by painter 2 relative to the change in the amount painted by painter 1. That is 1/4 of the way from that bar to the next bar. The blue bars, 1/4 of the way. How about this table right here in front of me? Gina, did you have a strategy for this?
I just found it the new, but I just didn't put the same as how we did the last point. So the X is 750 and the Y is 1,025.
Okay, so you added to this table
Yeah.
750. Okay,
Fine.
and then what?
That comes out to 30 over 41
Okay,
for the X over Y.
so we wanted to talk about the.
From the last point.
So, Lauren, do you have a strategy for this?
I found the rate of change between where the painters are at now from their initial
Okay.
starting point, and that gave me 5/4, and then I took the rate of change from how we had the change in Y and the change of X, and that was also 5/4.
So give me the details. So what did you do to get 5/4? You said you got 5/4 twice. So
Well,
give me the numbers. What are the
Painter
numbers?
2 is now at 1,025 feet,
Okay.
and Painter 1 is at 750. And so I took the change in the ending, the change in your final values.
Okay, so you looked at a change in what? Change in X or change in Y?
Well, change both.
So just spell it all out. Tell me everything. Tell me everything.
Well, I took the change from the final of Painter 2, which is Y, from the initial point of where he started, which was at 400.
Okay. Which was what?
625.
Okay, so we got a change in Y of. You're looking at from the start to all the way to the finish.
Yeah.
And you got a change in Y of
625.
625. Okay.
And then I did the same thing for the X, which is Painter 1. Oh, sorry, I'm backwards. Painter 2 is 500. The change in Y.
I thought you were starting from here all the way to here.
No, okay, I'm right. Sorry.
2, 3, 4, 5, 6, 25. Yeah.
It's been a lot of days.
Okay.
And then for Painter 1, the change in X is 500.
Okay.
And that ratio,
Okay.
the change in Y compared to the change in X, is 5/4.
Okay. And you said that ratio was
5/4.
okay. So, is it maintained? Is the ratio maintained? How do you know? It's only one ratio. Is there more?
So I did. You have to have that compared to something now in order to tell if it's.
Right.
Yeah.
I'm waiting for you.
So I compared it to the initial change in Y and change in X that we found. Which
Okay.
The initial change in Y was 200.
Okay.
And the initial change in X was 250. Well, I guess that gave me 4 bucks.
You have it right,
We
but
did it
so it's fine.
Do I have something written incorrectly?
No, you wrote it right. She just said it wrong, but you wrote it
It's 5 fours.
So it's 5 fourths.
right. No.
Yeah, change the y over change the x is 5 fourths.
Yes.
Okay. Anybody else do something differently?
You also did the change from the first time they stopped to the second time.
Okay, so there's another change here.
Yep.
Tell me, Lee.
And so from pair 1, you said he increased 300, so the change in x was 300.
Okay.
And then it looks like 375 was a change in y.
Yeah, that was halfway, and I told you that was a quarter of the way. Yep.
Okay. And the delta y over delta x will also give us 5 over 4.
Okay, so we have this number 5 fourths, 1.25. And this ratio is being maintained. I mean, any change, it looks like any change that painter 1 paints is the same size relative to the change that any amount that painter 2 paints is the same relative to the amount that painter 1 paints. And so is the total amount, is y, the total amount, changing at a constant rate of change with respect to x or not? So the ratio of x over y is not equal. The ratio of delta y over delta x is equal. Is the total amount painted by painter 2 varying with constant rate of change with the total amount painted by painter 1? Talk at your table. Yes or no?
I did all. Yeah, I did all.
Yeah.
No, it was just a statement.
Basically, it's
Okay, let's. Is y changing at a constant rate with respect to x? Yes or no?
Yes. Yes.
Okay, they say yes. What about you guys? You're saying no.
Say it again.
Does y change at a constant rate with respect to x? Does the total amount painted by painter 1 change at a constant rate with respect to the total amount painted by painter 2? Other way around. Painter 2 with respect to painter 1. They say no. How about up here?
You said yes.
Yes. This table. Think yes. Okay, so a little bit of dissent in the classroom. How could we, what do I need to do to this visual to apply maybe our more familiar way of graphing with horizontal and vertical axes? So how could I adjust or make a change to this visual so that it would then apply to graphing in the Cartesian plane, xy coordinates? Daniel.
You can use P1. Well, you can plot the points and see how, like at each point, well, at each different time, how y relates to x. So, like making x your x-axis, or P1 divides with P1 your x variable.
Okay.
Making P2 your y variable.
So how can I bring the bars into this? So what would I need to do to the bars? Instead of just plotting, well, we got ordered pairs, we can plot points. But what can I do to the bars?
You could change your orientation of your bars.
Okay.
So that your y bar was up, like straight up and down, like we would have on our x and y plane.
Okay.
X is horizontal and y is vertical.
Okay.
And then, as far as where it would be,
Where should I put that vertical bar?
at the end of the x bar. So on the far right side of the x bar.
So he's proposing that I take the blue bar, the y bar, turn it upright, and stick it on the end of the x bar, the right hand end. With that left. Oh, I didn't want to do that. Okay, well I'm gonna do what Tyler said. So I just took that bar and I flipped it up, and like Tyler suggested, I would put it on the right end. And now I'm gonna increase the amount that Painter 1 paints, and Painter 2 will increase likewise, just as it did before when they were both horizontal. Okay. Will this create a graph that you can work with? No. Why not? Is the length of the gold bar the x-coordinate? Okay, is the length of the blue bar the y-coordinate? So is this different than plotting points x, y? Let me zoom out. So I ask you, is this from here to here, is that the current value of x? From here to here, is that the corresponding value of y? Is that how we normally plot in the Cartesian plane? So where would we look at in terms of creating a graph now? Where do we look? Yeah, so, right. Okay, so I have another version of this. It's a little better for that. So again, same bars. And so we started here at 250 and 400. 250, Painter 1 painted. 450 square feet was painted by Painter 2. And we said we increased Painter 1's amount by, was it 200? Oh, brother. There we go. And we got a ordered pair of values. What ordered pair of values did we get? So that point on the graph represents corresponding quantities of those two values taken together, right? 450 painted by Painter 1. Was it 650? And then we increased Painter 1, or the gold bar, by how much? 300 from here? Which takes us to, was it 750? Oh, God. And we got another corresponding pair of values of painted by Painter 1 and Painter 2. We had that one to start. Okay, is it fair? All right, so let's go back to that first one, and I want to now I want to increase the amount that Painter 1 paints by 50, right there. So how can I represent that on the graph? An increase Painter 1 of 50. Crystal. Yeah.
Is
Painter 1 is our x coordinate, the yellow gold. Yep.
Okay. Yeah, so
Okay, so that's a delta x of So what did we find the amount, the corresponding change by painter 2 we found was relative to the change of painter 1? We found was what value? 5/4. So how could we easily compute the corresponding change of painter 2? Would be painter 2 is always painting, his additional amount painted is always 5/4 of what painter 2 additionally painted, right? So how would I calculate this? Wouldn't I take 5/4 times 50? And so then what does that change in y? 62.5. So now how much has painter y painted? So how can we easily figure that out? So we want to know now what's the total amount that painter 2 has painted. Right, so it'd be the old value of y plus the change, which equals? And so now that gives us a new point, right? So what's our new x now? 300, and our new y is 462.5. So that gives us a new point. Why? Because the additional amount painted by painter 2 is always 5/4 times whatever additional amount painter 1 paints. So this is kind of the key step here. Okay, so I want you to do that same thing. So let's draw that. So there's that change in x and then corresponding change in y. So we found the delta x, we found the change in y using this number 5/4 to get the change in y, and then we found that new y coordinate. All right, so I want you to do that again let's start here, and now let's do a change of x of 150. So what was that original point? 450, 650? You're doing a change in x of, so painter 1 from here, painter 1's going to paint an additional 150, and you're going to work through this process again to find the new amount painted by painter 2. So an additional 150 starting here at the point 450, 650. Okay, Carla, how'd it go?
So the change in x was 150.
Right.
So we know that to get the change in y, we have to multiply the change in x by 5/4.
Okay.
So that gave us 187.5.
Okay.
Which is the change in y, and you have to add that to the original 650 to get the y value, which is 837.
I heard it all. It sounded great. So you're going to add that change, you said, to the...
To the original Y position, which was 650. To get the...
All right, so we're going to... If we go 150, it's like this. And what was the final value of Y, just so I can draw this right?
837.5.
Something like that. So the delta X,
Was delta X was
150. Delta Y,
187.
and then to get the new Y, you took the starting Y, 650, added the 187.5. Yep. New ordered pair,
600. 837.
let's watch it happen. Here we go. Ready? Here it goes. What did I do? Zoomed out. Maybe this will correct it.
That's a different.
You clicked a different
Oh, that's easy fix.
There you go.
Whew, everyone take a deep breath. Okay. So let's watch it happen. Here we go. Can I stop in the right place the first time? Of course not. We've requested many times that you could toggle with the arrows instead of having to slide through the end slider, so you could just do one thing at a time.
Or you could just punch in coordinates.
What's that?
Or you could just punch in coordinates. That'd be nice.
Right. Yeah. He's been on it. Okay. So so we're creating this locus of points. How many points could we create? Yeah, infinitely many. Okay. So if we thought about every change in X that painter 1 could have, and the corresponding change in Y as giving us a point, how would the graph emerge? How would the graph emerge if we generated every point by looking at every change in X and corresponding change in Y? Well, before I do that, let's go back to our question. Is Y changing at a constant rate with respect to X or not?
Yes.
And so those who were saying no before, are you saying yes now? What changed your mind? Maybe, so let's ask it again. Is Y changing at a constant rate with respect to X? So is someone brave who said no before willing to say, this is why I changed my mind?
So I didn't say no, but I think the thought is that the proportion between any one point and another is not equal. Therefore, that's not constant. But the changes themselves between one to the other.
Okay. So when I ask that question, does Y change at a constant rate with respect to X? Was there a maybe the meaning of that was challenged? Is that kind of what we're saying? So Zach, what do you think?
Well, yeah, I hear those two different things. I hear that as you take the overall Y compared to the overall X, and that will be different every single time.
Right.
But after you pass that, the point that we were given, it's not the change is always the same. So it's a constant.
Yeah, the relative size of the change to the other change. Yeah, so the moral is that the ratio of the total Y to X is not a test for constant rate of change, right? What's the test for constant rate of change between two quantities? If the relative size of the change of one to the other is maintained. In this case, that relative size of the changes is 5/4, right? So how will the graph emerge? If I let X just start painting, or yeah, it's just painter 1 start painting, and painter 2 is going to paint, and this is going to generate points, what will we get? Okay, what's the slope of the line? Is it 1.25? 5/4? Does this line have a steepness of 5/4? 5/4 steep. Slope a measure of steepness? Here's a steepness of, oh jeez. Here's a steepness of 5/4. That red line has a steepness of 5/4. But isn't that what slope is a measure of? Tell me why not. What is slope? Slope is not steepness. What is it? Melissa?
The change. The change between X and Y.
Change between X and Y. I want to be more precise than that.
Rate of change.
The rate of change? So the slope is the rate of change. Slope is the constant rate of change, right? So this proves that you can't accurately have any visual connection to this idea of slope. It can only mean this value, right, of the constant rate of change. In this case, 1.25, because this red line has a steepness of 1.25, and so what is causing our line to not have a steepness of 1.25? Scales are different, right? And we can mess with the scales to get this to be any steepness. Does the rate of change change? No, the slope stays the same. Constant rate of change stays the same. Okay, so let's turn that off. So let's start at this first point. What was this first point again? Okay, so we were working through a process to get a new value of y by starting with a known change in x. Instead, let's just say that this. I'm just going to pick a point right here. And rather than say that has particular values, let's just say it represents any point on the line. I just happen to highlight this one, but that could represent any point on the line. So then what could I label that ordered pair? If it could be any set of corresponding values. No, but it can be any. It could be here, it could be here, 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 all of them. So how could I label that? Just generically x and y, right? So x could take on every x value, and then the y would be the corresponding y value. So now we're going to march through that same process that we used to find a new value of y. So our goal is to find this new value of y. What is this? Given this starting point, 250, 400. So what comes first? What comes first?
What was the question?
So was there a question first?
Yeah, I didn't hear the question.
So in the previous kind of segment, we worked through this process of taking a change in x in order to find the new value of y. So now rather than have a known change in x, I want to just pick any point on the line. This xy could represent every single point on the line. So now we're going to start here, and our goal is to find the value of that new y value. I think Alfredo was going to do it. Go ahead. Yeah, and what is it? What is it? Starting here and ending here, which this could be any point.
Oh, so it'd be, yeah, that x minus that 250.
Agreed? Okay, then Sarah, what would the change in y be then?
400 minus y minus 400.
No, we want to use that change in x to get it like we did before. So based on that change in x, how much does y change?
5/4 times x minus 2.
There it is. And so now we want the new, how do we calculate the new y? Tell me. Right, so we're going to take 400. So what did we just represent? We just represented the y value for any x, right? So this is representing every xy point on this line. We know where everything came from, right? X minus 250 was? Change in x. Corresponding change in y. 5/4 times x minus 250. And then to get that new value of y, we take 400 plus that change in y. Okay? So if we could start from any point A, B, that's a known point. Then we get what's called point slope form. Y equals m times x minus the starting value of x plus starting value of y. So we could write this exact same line. We'd use that second point that we found. What was the second point we found? 450, 650. So we could put 450, 650 in here, but our constant rate of change or our slope is still 5/4. That would be the exact same equation as that one. You'd generate the same locus of points, x, y. Okay, so I have a task for you. So any questions? So the next task is going to kind of show a very useful application of point slope form and why an advantage or a couple advantages over mx plus b. So mx plus b is still valid. It's just a very narrow view of constant rate of change. So this is another way to look at constant rate of change through the lens of changes, right? So delta x, if we know the constant rate, we know what delta y is, and then we can get any y given a starting y. So, in light of my perceived boredom in your faces, here you go. Here's a nice problem for you.
Jacuzzi.
All right, so a jacuzzi, small whirlpool, holds 550 gallons, and it's square in shape. Okay, it has a step on all sides for sitting. So this is like if we cut that thing vertically in half, you're looking kind of at the side cross view, cross section. The height of the step is 16 inches, measured from the bottom when filling the jacuzzi. At first, every 20 gallons makes the height rise 2.5 inches until you reach the step, after which 20 gallon creates a rise in the water of 0.9 inches. So I want you to write a function for the height of water in inches with respect to the number of gallons in the jacuzzi. This is your task. Go.
So like if you look at it from the top, it's a square, right?
Yeah.
Yeah.
Yeah. Yeah. So it's you got a square, square overall shape, and then a square step that goes all the way around. Yeah.
Just the step 16 inches or the whole thing 16 inches?
The step is 16 inches.
Bottom up.
You're not giving that information. step is step. Step is 16 inches from the bottom. The height of the step is 16 inches measured from the bottom of the pool. The height of the step is 16 inches measured from the bottom of the pool.
I don't know what this really looks like to be honest.
We'll get you the number of basically X value.
Where's so from 0 to first 16 inches. 16 inches. What's 16 by? So our number of gallons is going to be our X. So we don't care what that is. That's what we're going to do. That it could be infinite. But you know, it could be many X's. So we don't care that much.
In progress. Because when it says 20. Someone's using something they learned. Good. Or if you learned it. Anyone start by writing down the quantities involved? What the key quantities are? So, Tori, what'd you say?
I said there's like for every 20 gallons goes up 2.5 inches for the first
So yeah, I think you were hearing what I said. You're hearing that as did you ever write down any numbers? What quantities? Those who've been pathways. What do we mean by quantity? What's that? Yeah, so characteristics, measurable attributes, right? Attributes. So what is our X quantity? Number of gallons. And Y is?
Height of the water in inches.
Height in inches. I don't have room, but it's the height of the water. So if we're going to do a function of height with respect to number of gallons, then we want number of gallons to be X, input, and Y is our output, height in inches. So let's generate some pairs here. 0, 0, I heard. What else? Anybody figure out the number of gallons in the bottom part? 128, good, 128. So therefore, when X is
16.
128, Y is
16.
550.
34.99. So 35.
And what other information do we need here? And we're ready to write the function. Okay, tell me, Daniel. Did you get it?
Well, delta, for the bottom half,
Okay.
it's 16 over 128.
Okay.
And then the bottom, the second half would be 35 minus 16 over 550 minus 128.
Well, so you could do it that way, but you also know that every 20 gallons creates a rise of 0.9.
0.9 over 20. Whatever.
So what's going on here in this function? What's this function going to be like?
2 lines.
Right. So we're going to have this initial. And so here's where this point slope for. So let's define this function. What do you want to call it?
J.
J for jacuzzi. So J of X. Okay, so when we write G, so some of you said 2 lines. So we need what's called a piecewise function. For a certain number of gallons, the rate is a certain constant rate, but then we hit, after 128 gallons, then the rate switches. Okay, so we need 2 linear functions. So here's how you do that in GC. So you set up your function equals, and then if you have Mac, you do Control A, and if you have PC, you do Control Shift A. Now, if you want more lines than that, then you just keep hitting Control. Every time you hit Control A, you get another line. Every time you hit Control Shift A, you just keep getting more and more lines. We just need 2. So, check out how handy this is. Watch. So in this bottom portion, what's our slope? 0.125. Do we have a nice convenient point to use? Yes, 0, 0. So we go 0.125 times x minus 0. Maybe. Plus 0. And then, so, but we have to, this is only true when what? If, right, 0 less than or equal to x less than or equal to 16. Is that right? 128. 128. Our number of gallons is our x coordinate. So watch how easy it is to write this using this form. What's our rate of change? 0.045 times x minus. So all we need is a point on this line. 128. Plus. Okay, so, and where does 16 come from in this function?
The height of the water, 128 gallons.
Right, how can we represent that, the height of the water when there's 128 gallons? How can we represent that? Anybody? Besides 16.
Oh, F of 8.
Yeah, you got it. J of 128. Right? Isn't that this? So this is our number of gallons that we're gonna, this is the height that we're gonna start from at 128 gallons, and we're gonna add the change to that, right? Because this is this m times x minus a. That's our change, right? Change in y. Isn't that our change in y? Plus the starting y, which will be where we left off at 128 gallons. And so then we write if 128. Now we have to do strictly less than x. And then we said how many gallons total? So, do you see how helpful this, when you have to piece lines together, do a piecewise function like this? This is one huge advantage to this point slope form. Because you can just take the last point that you were at, and that becomes the new point on your next line. And then you can use the function recursively, so when it goes to this line, what's it going to do? It's going to take J128, and it's going to say, oh, it's calling upon J. It's going to put 128, and where's it going to go? Which line?
First line.
First line. It's going to crank out that 16 inches by putting 128 into that first line, and then we'll add 16 inches to the height. Okay, so let's graph it. I'm going to owe you a whole class of time, and I will honor it. Okay, so let's do it blue. Okay, so check Blackboard after 5 today. You'll have all the details of all the things that are due. Yeah.